thank you, Mike, for that introduction, and thank you for the organizers to give me this opportunity to talk here at All Things EFT. I think it's been a really great series of seminars. So last week we had heard from Julio, who's a friend and collaborator, talking about some generic features of massless scalar effective field theories. Today I'll be talking about the other end of the spectrum, where you have a massive particle, in particular when there's a very heavy particle, and we don't simply integrate it out, but keep it in the theory. And I'll also be trying to combine this generic set of field theory with some on-shell methods. And I'll apologize in advance because I won't be able to give credit to everyone who's been working on this area or adjacent areas, and sometimes I won't even try to list all the references. So I'll just put up a very biased list of work that I've been part of. And I want to highlight my collaborators on this, which I think are in the audience. So in particular, Kees Haddad, who's a postdoc in Sweden, as well as Rafael Aude, who's a postdoc in Belgium. And we've been working on these ideas for a few years now. So my background is in particle physics and in trying to combine techniques from both effective field theories and also more like modern methods in scattering amplitudes. And to this audience, I probably don't need to motivate why the use of effective field theory is a good thing. It has a very large range of applicability. It's a very generic and powerful set of ideas. And my view is that if you can use an effective field theory, you should use an effective field theory. But the second area that I've been working on is this amplitudes, or these modern methods in amplitudes, which is sort of like a loose collection of ideas developed throughout the last 30 years, plus some resurrection of very old ideas. And they'll try to tackle calculation of amplitudes from new and different angles. And these two fields are distinct, but there's substantial overlap as well. So, and if you combine the ideas of effective field theory with these methods from amplitudes, you might be able to develop new theoretical techniques, which might help improve your calculation ability and hopefully have some insight into the problems you're tackling. And with these tools at hand, we want to apply for something that's relevant for the physical world. And the most exciting part of as a theoretical physicist is if you can use calculations that are relevant for experiments, and especially when there are new experiments exploring like new frontiers. And all this, these bullet points can be summarized or are relevant for the main problem that I'll be tackling today, namely the binary inspiral problem in classical general relativity. So what is the binary inspiral problem? So the binary inspiral problem is a classical problem, and it's the problem of how does two massive gravitationally bound objects evolve through time. So these guys can be either, say, two black holes, or two neutron stars, or a black hole and a neutron star for our purposes, and they move around in a bound orbit at normal relativistic speeds. And as they're moving around, they will emit some gravitational radiation, and the size of their orbits will gradually shrink. And then they hit, at some point, they will hit a phase where they merge, and then eventually settle down into a new equilibrium as a one-body object through like a ring down phase. And this process is very interesting by itself, but it's even more interesting because it leaves behind a signal in terms of gravitational radiation. And this signal can actually be observed. And it's been a very, very great success by experimental efforts to observe these gravitational radiations. And the signal takes like this characteristic form that there's some almost periodic signal in the inspiral phase. It will then gradually increase up until the merger point and then go down again through the ring down. And these gravitational wave signals have been observed ever since like 2015 and continuing up to today through great effort by the LIGO collaboration in the US, Virgo, Europe, and now also the Kaggle collaboration in Japan. We have multiple sets of gravitational wave observatories spanning several continents. So, and all these observatories feature like a basic design where they have like it's a very, very large interferometer, which you can see in this picture here, where it has these two long arms, which will detect when a gravitational wave passes through the interferometer. But because of these experimental achievements, the theories need to keep up as well. So we need to, in order to learn something from these experiments, we need to compare the measurements to theoretical predictions. And for those, we need theoretical tools. And there are several tools that are being applied to this problem. And here I'm just listing a few. Like one tool is to just use numerical relativity. That is to say, solve the Einstein's equations numerically on the computer. And that's an essential tool for this problem, especially in the merger phase, where the gravitational fields are strong. So one can't use other perturbative calculations to do it. You simply solve it numerically. As with any numerical simulations, it might get expensive to run if you want to run the simulations for longer and longer periods. And that is like if you want to capture more and more orbits before the merger phase, that can be quite expensive. And in that regime, namely the inspiral regime, we would like to use other methods to help out the numerical simulations. And some of those methods can be, for example, what's known as self-force, which is a way of solving, it's an extension of solving the geodesic equation for a test particle in a fixed background. This is not an unusual perturbation theory in the coupling constant, but it's in the perturbation theory in the mass ratios of the two objects. So like the leading order term is solving the geodesic equation, which gets you all everything coupling the leading order in the mass ratio results. And then the self-force is like how to systematically improve that calculations. A second method that can be applied is what's been well coined the non-relativistic general relativity, NIGR, by Goldberg and Rothstein, which is a way of tackling the problem by treating these, say, two black holes as two non-relativistic world lines interacting with gravity. And the ideas behind this formalism are very philosophically related to the ideas that I will be discussing later on. Namely, they're coming from heavy quark effective theory or non-relativistic QCD, just applied to gravity instead. Yet another approach is to use what's called the effective one body, where instead of treating these two objects as two world line, one treats the whole problem as like one object moving in an effective background or an effective metric. That was pioneered by Demore and Bonanno. And then lastly, over the recent years, many people have been applying techniques from scattering amplitudes to this problem. And this is where I'm also coming in, and this is where I'll be focusing the rest of the talk on this application of scattering amplitudes to the classical binary inspiral problem. And you might immediately have some questions about that. So I'm saying I want to use scattering amplitudes to solve this classical GR problem. So just to list like a few objections you might have right off the bat. You might ask, like, why you want to calculate classical physics, but you're using quantum field theory. So how can you, or how is that done precisely? A second objection might be that the binary inspiral problem is a problem of two bound objects in orbit, while a scattering amplitude calculates like probabilities in the scattering experiment. Namely, you send in things from infinity, they interact, and they fly off to infinity again. So it looks like they're just two different physical setups. So isn't the amplitude answering a different question than the one that's being asked in this bound orbit? And then thirdly, are we talking about black holes, or are we talking about particles? They are, one is very large, one is very small. So there might be some questions there as well. And then lastly, like, even if hopefully I can convince you on these other points, like, why even use amplitudes? Why is it beneficial to use amplitudes in this problem? So let's deal with this one by one. So first of all, how can we use quantum field theory for classical physics? And this is more of a technical question than an actual obstacle, because, like, of course, the world is quantum mechanical, and there's a limit where classical physics emerges. So it's just a question of how to take that limit in practice. And to do this, we will apply a two-step procedure. Like, first, we want to make contact with things we care about in classical physics from the things we calculate in quantum field theory. And then you might want to take a classical limit, maybe like h bar goes to 0 limit, to only keep the terms you care about classically. So let's first see how to connect scattering amplitudes to something that is classical. And let's just start with the simplest scattering amplitude we can think of that might be relevant for the problem at hand. Namely, we have two, let's say, scalars coming in, exchanging one graviton, and then flying off again, where the exchange graviton exchanges momentum of q here. And this simple QL amplitude takes on a very simple form. I mean, it's just 1 over q squared from this graviton propagator, and some factors in the numerator coming from couplings and so on. And if we take the Fourier transform of this amplitude from q space to partition space, we end up with a 1 over r. And this is nothing but Newton's potential. So this very simple tree-level amplitude contains information about Newton's potential, which is clearly relevant for classical physics. So there's a link here between things we calculate in amplitudes and things we care about classically. That was step 1. Next, step 2 is we're going to take the h bar goes to 0 limit. And in order to do this, we need to see where all the h bars factors enter in our calculations. And a very nice work by Kosover, maybe, and O'Connell explain how to reintroduce the h bars in the calculation with scattering amplitudes. And instead of just using natural units where h bar equals 1, we want to introduce the h bars. There's some h bar coming with coupling constants. That's not that important for us at this point. But what is important is that there's distinction between massive particles and massless particles. And in that, the massive particles, we want to keep their mass and momentum fixed, meaning like it doesn't scale with h bar. While for the massless particles, we want to scale the momentum of massless particles with h bar. So it's like the wave number that's kept fixed, and it's like this additional h bar here. A different way of seeing it is you want to say that you want to scatter off two guys which are like point particles, and they're separated by a long distance, like a very large impact parameter. And this impact parameter is conjugate to this transfer momentum q, and that's where this difference in scale is entered. Let's just put back the h bars in our calculation. So in the scattering amplitude, we had some h bars coming from this property, from this q, as well as from the coupling. So it's overall the amplitude goes as 1 over h bar cubed. And that might look scary because it diverges in the classical limit, but fear not. Let's just put it back into this Fourier transform. We see from the Fourier transform itself, there's an h bar cubed hiding, which will cancel this 1 over h bar cubed. So the classical potential has no h bars left over, which is what we expect. And this can be extended to include like higher perturbative correction to this calculation, and so you know which terms to keep and which one to throw away. That was the first objection. The second one is like, what about this? Like, is it the bound orbit, or is it this unbound scattering event that we really care about? And it is a good point, because like the actual physical system is a bound orbit, while the thing we calculate it is unbound trajectory for scattering amplitudes, and they are just different things. But the important point is that the information that we can extract from the scattering event can then be used to gain information about this bound orbit. And you think of it as like when these two, say, black holes like scatter off each other, they will interact through gravitational exchanges. And it's the same kind of gravitational exchanges that are relevant in the bound orbit as well. So we just need to like take the information we can get from the amplitude and translate it into things that can be used for the bound scenario. And one way to do this is to go through the Hamiltonian. So here's the Hamiltonian for these for two objects in the center mass frame interacting through some potential V here, and this potential have these like unfixed form factors, and you can include like higher and higher corrections in G Newton in this potential. And like a priori, these form factors are unknown, and that's what we want to like fix. And one way to fix these form factors is by doing a matching calculation like from this Hamiltonian and match it to the amplitude we calculate from scattering amplitudes, and that will like fix these coefficients for us. And once we have this Hamiltonian, we can then use that Hamiltonian to calculate bound state observables. This is a very nice way to go from the amplitude to the Hamiltonian and then to the bound state. And there are other methods that doesn't take this route. So you can do many things. So here's just a few. You can, for example, you can calculate observables directly from the amplitude. This is explained by Kosler, maybe, and O'Connell. You also might want to go through what's called like the iconal phase, which is related to the amplitude. And from that iconal phase, you can calculate various observables as well. Another very interesting set of relations was developed by Kelly and Porto, which, like through some analytical continuation, they found like several maps between observables in the unbound case to be related to the same, like to different observables in the bound case. Like for example, the scattering angle is related to the Perry-Aspen advance from the unbound to the bound case. That's one example. And then lastly, as we were seeing, the Hamiltonian can be used as an intermediary for these different scenarios. Good. That was point 2. Now point 3 was, okay, do we talk about black holes or do we talk about particles? And like before answering that, I can ask like, what even is a black hole? And you might get different answers depending on who you ask. So if you ask an astronomer, they might say that, oh, this is a black hole. Here is a picture of a black hole in the center of the Milky Way, taken by the Event Horizon Telescope. And if you ask a general relativist, they might say, oh, this is a black hole. Here is the metric space-time outside a spherical symmetric body named the Schwarzschild metric, describing a non-rotating black hole. And what I will try to convince you, or if you ask me, I might say that, oh, this is the black hole. Namely, this is the leading interaction between what we think describes the dynamics of now a spinning black hole linearly coupled to gravity. So this is encoded in the scattering amplitude between these 3 points of one incoming massive guy, outgoing massive guy, and one graviton. And it takes the form on the left here. You have this prefactor, which is the scalar, or the amplitude of a scalar coupled to gravity, times the exponential of q, which is the momentum of the graviton, dotted into the spin of the black hole, or the ring radius in this case, of the black hole. So, and this amplitude here, like all the spin information is contained in this exponential factor. And we have good reasons to believe that this corresponds to the dynamics of a curved black hole. Good. And then the fourth, so we'll hopefully we'll get to explore this relation in more detail, but we'll need to develop some formalism in order to digest this equation further. And then the last point was like, why should we even use amplitudes? So one very simple reason to use amplitude is that like the amplitudes are relativistic while the bound orbit is non-relativistic. And this means that when we calculate the scattering amplitude, we'll get information which contains like higher velocity corrections as compared to this non-relativistic calculations. And that means that the amplitudes like naturally resum many of the terms that we need for this bound orbit. This is often referred to the post-Minkowskian and post-Newtonian expansions. I probably won't use these terms in this talk, but it's sufficient to know that the amplitude is one single expansion in the coupling constant and not a double expansion in the coupling constant and the velocities. And that's one reason to use amplitudes. Another reason to use amplitude is that we, over the years, have developed many tools that allow us to calculate these scattering amplitudes to very high precision. And these tools have been developed, for example, in the context of QCD, relevant for particle collision at the Large Hadron Collider, but they can be easily imported to this new problem. And just to mention some tools that have been used is in order to calculate like higher loop amplitudes, we need to construct a higher loop integrand as well as the loop integration. And this higher loop integrand can be reconstructed through generalized unitarity which basically like takes this integrating and constructs it from like on-shell unitarity cuts, where you only need the tree-level amplitudes as input. And when you have the loop integrand, you need to integrate, and which is generally a very hard problem. But many like tools to do this integration have been developed, and they can also be just applied to this other to our case. And then there's also the double, what's known as these double copy relations, which is been very influential in the amplitudes community. That's a relation between scattering amplitudes in gauge theory and scattering amplitudes in gravity. And you can see this through like various manifestations. One is more like string theory inspired through the KLT relation. Others are the colloid kinematics duality. And it basically lets you go from a gauge theory amplitude to a gravity amplitude. And since we want to use gravity amplitude, that's very nice, that's the output, while the input, the gauge theory amplitudes, are in general much simpler to calculate. And then lastly, of course, effective field theory is really important. And this binary inspiral problem is a multi-scale problem. So applying effective field theory is essential. And there's been many results and works now applying these amplitudes methods to the binary inspiral problem. And I won't list many of them, just to mention a few. Great work by C. Byrne and collaborators have like pushed the state of the art to very high loop order now. It's like ordered G to the 4 for non-rotating black holes, which are modeled as scalars in these calculations. And just yesterday there was a paper out doing the G Newton cubed and spin squared dynamics, just to show that it's a very active, very flourishing field, and a lot of young people are getting involved, which I think is really cool. But despite this success, you might say, is there even more things we can do? Are there other tools from quantum field theory that we can apply to this problem? And yes, there is. For one thing, and there's an obvious statement that the black holes are much heavier than the interaction scales in the problem. And when there's this hierarchy of scales, it's useful to exploit it and take the heavy limit. And another tool which can be applied is to use on-shell variables to simplify calculations and so directly go to the object of interest, namely the amplitudes. And then maybe if I have time at the end, we'll see. There's also you can apply, if it's not a black hole you're talking about, but a neutron star, they can differ in that the neutron star can be a bit squishy, or namely they can be tidally deformed. And these tidal deformations can be modeled through higher dimensional operators in effective field theory. And as we've heard talks in this series already, that whenever there's talk about higher dimensional operators, you might worry that, do we have a non-redundant basis of operators? How do we count them? How do we construct the amplitudes? And a very useful tool to do this is to apply the technique of the Hilbert series. This has already been applied to the standard model effective field theory, and the same tool can now be applied, but for like the tidal operators of neutron stars. And some of the results using these additional tools, I just want to highlight the work by my collaborators and myself, where we calculated or the G Newton squared and all orders in spin dynamics, where we heavily relied on this heavy limit and Anschel variables. We also applied this Hilbert series to tidal effects. So yeah, that would be our target to sort of digest these results. And so let's just get into it. So the heavy limit, or the heavy particle effective theory, has its prime example in heavy quark effective theory. And we have like several talks already in this series about this from many of the experts. And the basic idea is that we have like one heavy quark with mass m interacting with light degrees of freedom, like other quarks or gluons. And the interaction scale is much less than the mass of the heavy quark. And when that's the case, it's very useful to decompose the momentum of the heavy quark into two pieces. So that we want to write P equals mv plus k, where mv is a large part and k is a residual momentum, or like small part compared to m. And then we expand in k over m. Let's just quickly go through the derivation of from QCD to HQT. So we start with fermion coupled to gluons, like here. Then we split the field, the fermion field, into two components, like Q and Q tilde, where they're defined through these projection operators, like 1 plus v slash, 1 minus v slash. These projection operators will be relevant for us later on, so keep them in mind. Then we just plug this back into the Lagrangian, and we get terms which depend on Q, some which depend on Q tilde, and some cross terms. But note that the Q term has like no mass term, while the Q tilde term does. So we want to like remove the Q tilde fields from our theory, and this can be done by like integrating out the fields. And at 3 level is just using the equation of motion for the Q tilde field. And if we do this, we end up with an effective field theory only involving the Qs, taking this form here. And if we expand out to the first few terms, it takes the usual HQT form here. So the HQT Lagrangian is an expansion in one over mass. It also like illuminates the structure of the theory, namely it provides like a multiple expansion of the fields, where the first two terms here are the same whether you started with a scalar or a fermion, while in the fermion case you have this additional spin orbit coupling here. So it's like a spin dipole coupling. But what does this have to do with classical physics precisely? Well, if we go back to the like H-bar scheme counting by Cotter and O'Connell, we knew that all the massless fields should have like an extra H-bar hidden in their momentum, making it small compared to the massive fields. While the massive particles just have a large momentum. Now in the HQT expansion, because the massless fields and the residual momentum are on the same order, we should also scale the interaction scale of the residual momentum by an H bar. So the large momentum P contains like one like large MV part and a small H bar K bar part. So the HQT expansion is an expansion in H bar K bar over M. So we must have that this relation is this, since we're expanding it, this has to be a small param. But also, like as a Cosper maybe in the column was explaining, in order to like describe these two black holes in terms of point particles, this hierarchy of scales needs to be satisfied. Namely, that the Compton wavelength has to be much less than the spread of the wave packet. Just describing these black holes as some wave packet that peaked around the world line. and that's much less than their separation or their impact parameter. And just from the definition of the component wavelength, that's h bar over m, which we also see up here. And then lastly, like the scattering length, which is 1 over q, is on the order of the impact parameter there. This Fourier transform, and that's just this b and this q here. So we see that the h bar expansion precisely coincides with this outermost inequality for this point particle description to be valid. So that means that like heavy quark theory precisely gives us the right description that we're interested in. Now we can like repeat the derivation of heavy quarks, but now not couple the quarks to gluon, but couple them to gravitons. So just to refresh, we start in the heavy quark case by the QCD Lagrangian, integrate out the antiparticles, and we end up with this heavy quark effective theory. Now, in the case when it's fermion coupled to gravity, you might say that should model a black hole, so you can call them heavy black holes. And then we start with minimally coupled fermions to gravity here. And then we integrate out the antiparticle, and we end up with this heavy black hole effective theory at the level of this Lagrangian. And it takes almost the same format as the heavy quark, but just some subtle differences in their interactions. So that's the heavy particle effective theory. Now, I said we want to combine this with some on-shell methods. And for on-shell methods, I'm having in particular in mind.
Andreas, can I ask a quick question before on the previous slide?
Good, yeah.
Yeah, so how good is the analogy in the sense of if you went to like the non-normalizable interactions and you want to take the heavy quark limit on the one case and then the heavy black hole limit on the other case, does the analogy break down as you go to higher and higher orders just because of the different interaction terms that are allowed in the different cases? Or is it really a good analogy all the way up in mass dimension, if you will?
So you're asking about, if I'm understanding, how well does this Lagrangian here describe a black hole? Is that the question? Or... Well,
just in the sense of on both sides, you could think about higher order interactions, right?
Yeah.
And, so how good is the analogy as you go up in the order of the interactions?
Yeah, so the important thing here is that we don't need all the interactions. We only need like the first leading terms in order to calculate, because we only, so that goes back to this example. So because we're interested in classical physics, we only want to keep the leading few terms in this expansion, in this heavy quark expansion. Meaning we can suffice by taking this Lagrangian and expanding up to a certain order in 1 over m and ignoring the other higher order operators. At least for like, if you size with by low orders in G Newton, that's sufficient. So you don't need the full Lagrangian, you just need the first few leading terms. So the other one would be like quantum fractions.
I'm just curious how the analogy worked.
Mm-hmm. Yeah. Let me just continue because I'm probably a bit pressed on time. Yes, sorry. So the take-home point is that we want to exploit this heavy limit right from the start. And the second part, we want to combine this up with some on-shell methods, some on-shell variables, in order to not necessarily having to go through the Lagrangian, but just directly write down scattering amplitudes of interest. And to do this, we want to introduce some nice variables which describe the particles that we're interested in. And this done through what's known as the spinor helicity formalism, which maybe is most well known for massless particles, but it also works for massive particles. So using the notation by Arkani, Hamed, Huang, and Huang, one can introduce spinors for each momentum p, you can write these like angle and square bracket spinners that encode the information or the kinematics of that particle. So when you have a massive particle, or p squared equals m squared, these spinners have this additional capital I index. So that's like two components. While if it's a massive particle, you don't need this I index. There's only one spinner. And like these spinners transform nicely under the little group and so on. And they directly show up in amplitudes. So using these spinners that Arkani-Ham and Huang wrote down various amplitudes at 3 points for like two massive and one massless particle, where a very simple amplitude just contains this one monomial here. So you have a particle spin s, which could be a higher spin particle, coupled to either photons or gravitons. It's equal to this prefactor x, which is the scalar amplitude, times this spinner bracket 2, 1 to the power of 2s. So you need like 2s spinners for each spin s particle. And this is like the simplest thing you can write down. And this can be like named like the minimal amplitudes at 3 points. And these amplitudes will be important for us later on, or very soon, I say. Now that was for the massive spinners. If you want to like combine it with this heavy limit, we can go back to this relation between the fermions in the QCD case versus the HQET case. And these are related by this projection operator, this 1 plus v slash over 2. So you have like the massive spinners, or the heavy spinners here, and the massive spinners here. And you just like plug in this projection operator. You can then use the direct equation to rewrite this as 1 minus k slash over 2m, which you can take as a definition of these heavy spinners. Now that we can then introduce these on-shell spinner helicity variables for each of these spinners. So on the left-hand side, we have these p's, these I indices. And on the so that was on the right-hand side. On the left-hand side, we have these v spinners from this heavy guys labeled by their velocity, v. And note that there is no I index on these heavy spinners. That's just because I've contracted this I index with some auxiliary variable set on the right-hand side. So that's for like technical convenience, but you can relate these to like more physical reason is from coherence. Like if you want to describe like a coherent spin state, these like auxiliary variables take on the role of these coherent spin states variables. And then with these spinners, we also want to define like the actual spin of these rotating particles of these black holes. And that's done through the usual Paolo-Libansky pseudovector here, which is this contraction with the angular momentum operator and some reference p, some reference momentum p. And for heavy particles, so this p is like your choice, but for heavy particles, it's very natural to choose this p to be not incoming momentum or outgoing momentum, because they differ in the scattering process, but to choose it to be the large velocity of the heavy particle, which remains conserved throughout the scattering process. So in terms of on-shell spinner space, this definition is on this expression here. So this v is coming from our choice of putting like v here. And they have like two open spinner indices, alpha, beta. So they naturally will be contracted with these heavy spinners on the outsides. And if you normalize it like this, as well as divide by the mass, this expression takes on the role of the ring radius of the black hole. And at the end of the day, it's only this A parameter that would be relevant for us in the calculations. Like all the spinners, all these definitions sort of are souped up in this A vector here. And it doesn't care whether you use like angle or square brackets, because they're equal in this combination. Good. Now I can go back with these like spinners as variables for the kinematics. We can then start to write down amplitudes, starting at this lowest order, this 3-point amplitude. So we have like spin s interacting with the graviton. And the general amplitude takes this form. So you have the spin s amplitude here on the left. It's equal to this scalar amplitude, this h comma 0, this proof factor, times a sum over multiple spin multiples in the form of like q dot a with some a priori unfixed coefficients. This is the most general thing you can write down for the same spin at 3 points here. And if we sort of want to compare this or match it against these minimal amplitudes by Akarni Hamed and Huang, that just means that we need to pick these values for the coefficients as here. And if you just plug it in, you'll see that a bunch of these factorials cancel, and we're left with this 1 over k factorial q dot a to the k, which is nothing but an exponential. So this means that this minimal amplitudes, for these minimal amplitudes, all the spin dependence exponentiates like so. That's a very nice feature, and very interesting. And then what does it have to do with black holes? And the easiest way to see this is to match this amplitude against something we know it describes a black hole. And this we can do from comparing against the Worldline theory. So here's the Worldline theory for spinning with spin degrees of freedom on the Worldline, where all the spin is here as well as these spin multiples. And in general, there would be various Wilson coefficients for these spin multiples. But for a Kerr black hole, it turns out that they all would be equal to 1. So I haven't written out on this slide the expression for these spin multiples is in the appendix. And if we do then a matching calculation between our Einstein amplitude and this Worldline, we find that these coefficients that we wrote down on the Worldline, or here, are related to the coefficients in the amplitude here, like so. And for a minimal amplitude, you just plug this value back in. It turns out that these factors precisely canceling, you get back that all the spin multiples are equal to 1, meaning this exponentiated amplitude does describe a black hole or a spinning black hole. And then we can say, okay, let's go further. Let's do not just one graviton, but two. And if these gravitons have the same helicity, it turns out that the same thing happens. Namely, you can go from the amplitude with spin is equal to the amplitude with no spin times a factor where all the spin is exponentiated, like here. And this continues to be true for more and more emissions. Like if you have more and more emissions of like with the same helicity, like all that happens is that it goes into this all the spin goes into this exponential factor here by starting from like minimal 3-point and then recursing on that. But there's a problem if you look at the other amplitude where these two gravitons have opposite helicity and like a minus plus. It sort of like also exponentiates like here, but this factor in the exponential is kind of curious. Namely, this last term has an unphysical pole, and if you expand up to high enough orders in spin or ring radius a, you will eventually hit these unphysical poles, which is bad. But this is more of the artifact of the way we were calculating. So the way we got this expression was to use like on-shell BCFW recursion, which relates this amplitude to like by some complex deformation, and you through the Cauchy's theorem pick up all the rest of this elsewhere. But in that derivation, there is generically a boundary term, which is not being included in this expression here. And that means that the missing boundary term should cancel all these spurious poles. And in general, it's hard, like these boundary terms are annoying because it's hard to calculate a priori. But that's really all this is. Now, my collaborators and I found a way to like add back in this boundary term and fix the complement amplitude such that it has no spurious singularities. And this is especially, it becomes especially tractable in the classical limit where like some extra simplifications happen. And you can write down the opposite holistic complement amplitude in this form here, and it's based on some recursion relations. This is a closed form solution to those recursion relations. And now you traded the problem of spurious poles with a different problem, namely that there's an ambiguity in that you're free to add back like some contact terms C with unfixed coefficients. Those will then, those are part of the boundary term. But at least this is like a physical sensible object to study. And we want to say like, does this then describe a black hole? Or put it differently, which kind of contact terms are necessary to describe a black hole? And if you then take this amplitude and feed it into the full scattering of two black holes, like in this boundary, you would generically expect that the resulting amplitude should depend on the spin through various factors. So it could be, if you have one spinning, one non-spinning, the spin could enter as q dot a, q squared a squared, or this v dot a, where v is the velocity of the other non-spinning guy. But based on low spin data that we are relatively comfortable does describe a black hole, it turns out that these three structures are not all independent. Namely, like the resulting amplitudes have a dependence on q squared, q dot a squared minus q squared a squared with this relative minus sign, as well as this other guy. So instead of having three structures, you only have two. And you might then, and you also have evidence on the contrary that you want to describe a neutron star and start with a non-minimal 3-point, or like have a tidal operator which can spin, you will generically break this relationship, this minus sign. And then you might conjecture that, okay, this happened for a black hole, does not happen for a neutron star. Maybe this is true to higher spins, like higher origin spin. And this we put it as like an assumption or input into fixing the contact terms in our complement amplitude, and we just then plugged it in and calculated the relevant scattering amplitudes. So at next to leading order, it turns out that the relevant topologies are these triangle topologies here. These are not Feynman diagrams, but they are like unitarity cuts. So each vertex is its own scattering amplitude, and all these propagators can be put on shell to extract that. those coefficients. And the resulting order d squared amplitude can be decomposed into a term which is even in spin powers and odd in spin powers, here and here. And we were able to calculate these things in a closed form to all orders in spin, meaning like from like no spin to infinite spin. And they take like a very, very simple form. So here's the odd powers in spin expression. So M1 and M2 are coming from these two different topologies. And it contains like this infinite sum from k equals 0 to infinity. And all the spin dependents are souped up in these capital V and this Q. And all the Q comes enter as in these hypergeometric functions here. And then they're multiplied by some relatively simple form factors that depend on the relative velocity, which is here in v1.v2. So the resulting amplitude is remarkably simple. It only, like, by assumption, it only depends spin dependence on V, capital V and capital Q. And you might ask, like, is this a black hole? And that requires an input from something that we definitely know is a black hole, but it's very suggestive that this structure is there at low spin. And then, very surprisingly, like all these Q dependents resums into hypergeometric functions. And it will be very interesting to see if there can be some underlying symmetry reason for explaining this. And then each of these V's only can like one hypergeometric function F here. And lastly, like some of these quantite terms that we were adding back into the amplitude, they can be fixed if you demand an improved ultra-relativistic behavior for some of these form factors. And this calculation was done possible by use of these heavy spinners that we introduced before. And there are several reasons for this. Like the heavy spinners, I think, are great. For one, they exploit this separation of scales, namely this basic EFT idea. Secondly, because you have this conserved quantity, this V, you can then uniquely define this spin with respect to this V. And you don't need to like do like a Lorentz boost from one spinner to the other spinner to define the radius of the spin of the object. And related to this, there's this manifest spin exponentiation going on. And you can actually combine this up with coherent states to like more rigorously take the like infinite spin limit. And yeah, and we were able to calculate this all orders in spin using those variables. Now, I think I'll skip the tidal effects because lack of time. So I'll just jump right back into the summary. So I've tried to convince you that you can use quantum field theory to describe classical black hole dynamics. And essential in this is to use effective field theory techniques to include both spin and also tidal effects, which I didn't have time to discuss. And the combination of effective field theory and amplitude techniques lead to new results. Like here's just one example of G squared and all orders in spin results using this combination. And just an outlook for what's next, one can try to do, say, higher order calculations, go to next order in G Newton, and see if we can do something similar using these variables. Another thing that could be very interesting is to sort of like try to connect this formalism to the world line. So the heavy particle theory is like this happy intermediary between the full quantum field theory and like a classical world line. And full quantum field theory and the effective heavy particle theory, it's easy to see the link there, but like getting the direct link between this heavy particle and the world line, especially when there's spin involved, will be very interesting to derive. And then we can also go back to the roots and see if there are problems in heavy quark effective theory that can be tackled by using these heavy spinners. And maybe more speculative, like are there other areas in physics, maybe nuclear physics, where there are heavy things that also needs to or can be attacked through these formalism. So I just thank you for your attention.